Namaskar students, I'm Dr. Charu Devedi from Department of Chemistry. In this particular module, we'll be talking about the course, which is a discipline-specific elective course offered for 5th or 6th semester student, that is Novel Inorganic Solids. It is a 4-credit course. The mode of examination will be as follows. There will be one mid-semester exam of 30 marks, then end semester exam of 50 marks, and 20 marks are reserved for the internal assessment. The objectives of this course are to know and understand the methods of synthesis and modification of inorganic solids, and especially their applications as solid electrolytes and in mixed inorganic pigments, and also how to synthesize the nanomaterials of silver and gold, and what are nanomaterials in general, how they are classified, and why it is important to classify the nanomaterial based on their different physicochemical properties. Also, one of the main objective is to build an understanding on the composition and mechanical and fabrication process of the various engineering materials such as cast iron, plain carbon and alloy steels, FRPs, which we see around us all the time, and also to look into their environmental effects and what are their compositions and composition based applications. And the last objective, which is in the last unit of this course, is the understanding of ion exchange rays in their working, their applications, and also we'll touch upon the ceramic and refractory material and their applications. The expected course outcomes are as follows. We expect you all the students, to understand and know how the different modification and synthesis of inorganic solids can be carried out in the lab or even at the industrial scales. What are their applications, the futuristic and the current applications, and also to build, you're expected to build one understanding on the nanomaterials and know the synthesis of silver and gold nanomaterial by soft chemical methods or wet chemical methods. You're also expected or to understand the requirement of the composite material, their environmental effect, and how the market is being driven by the composite material these days, and what are ceramic and refractive material and their application, and how these materials are so different from other class of inorganic materials. The course content goes as follows. In the first unit, we'll be talking about the synthesis and modification of inorganic solid. Here we'll discuss 6 methods, which include conventional heat and beat method, co-precipitation, Sol-Gel, hydrothermal, ion exchange, and intercalation method of synthesizing inorganic solids of various types. The second unit will be make use of the understanding built in the first unit about the solid inorganic solids, and then we'll look into the application of these solids as solid electrolytes of all type, like cationic, anionic, and mixed solid electrolytes. We'll also discuss what are inorganic pigments, how these are different from the dyes which are of organic nature. We'll be focusing on few colored inorganic pigments, and the more emphasis will be given on white and black pigments, the types of inorganic material which are used as the white and black pigments. We'll also talk about molecular materials and fullerenes, the nanomaterials of carbon, the molecular material, their chemistry, 1D, one-dimensional metallic nanomaterials, molecular magnets, and inorganic liquid crystals. In the third unit, we'll talk about nanomaterials. So second and third unit will go together if you looking at the content, there is some overlap over the basic concepts. In this, we'll talk about the nanostructures and nanomaterials. We'll discuss a little bit of its history and the classification and the basis of classifications. We'll talk about the experimental methods of preparation of gold and silver metallic nanoparticles. We'll perform few experiments related to these synthesis also in our lab. We'll also discuss the self-assembled nanostructure and how the nano architecture control gives the different properties to different nanomaterials. Then we'll discuss in detail the carbon nanotubes and the inorganic nanowires, how the bioorganic and bioinorganic nanomaterials can be synthesized. And we'll also look into the natural and artificial nanomaterials and bio-nanocomposites. The next unit, which is Introduction to Engineering Material for Mechanical Construction, the content of this particular unit is a little bit different from what we would have discussed in the previous units. Here, we'll be talking about the engineering material which we see around us in general. From the chemistry point of view, we'll talk about their composition, their mechanical and fabricating characteristics, their various application. Will put emphasis on the engineering material based on iron, that cast iron and plain carbon and alloy and different alloy, including steel and alloys of copper and aluminium and brasses and bronze. And the cutting tool material will also discuss what are super alloys and how these are different from the other class of alloys. Then we'll move on to the discussion on the polymers, all the three types, the thermoplastic and thermosets and the fibers, and also we'll discuss about the composite. In the next unit, which is composite material, the introduction of the composite material, their limitations, their and why it is important to have composite material in today's day and age, that will be discussed. The conventional engineering materials, how these are different from the composite material, the role of metrics in composite, their classification, how these composite material can be further uh, made better by adding some reinforcements, uh, may it be fiber or nano platelet or fibrils. We'll discuss about these aspects, and we'll also talk about the mechanism of the reinforcement which these material, the reinforcing material, provide to the main matrix of this composite. In the last unit, we'll be talking about specialty polymers. First, what are the conducting polymers, the conduction mechanism, polyacetylene, polypropylene, and polypyrrole are the chosen examples of the conducting polymers for this semester. Their various applications will also be discussed. We will also talk about the ion exchange resin and their application, and what are ceramic and refractory materials, how these are prepared, what are their raw materials, and how these are completely different from the other materials used in construction work. So for this course, you may refer to the reference books listed here, Shriver and Atkins, Inorganic Chemistry by Shriver and Atkins. That is one book which will be referred to for this course. Another book which is Solid State Chemistry and its Application by A.R. West, especially the unit 1, 2 and 3 will be having some discussion from this particular book. Callister's book is also a very important book for this course. Its title is Material Science and Engineering, an Introduction. This book has all the content for the units which are appearing later in the progress of this course, that like specialty polymer, composite material, and materials used in construction and for engineering purpose. The Introduction to Solid State Physics by Charles Kettle is also an important book which will help you to build an understanding about the solid state solid state materials, the crystalline materials and inorganic solids. So, in this module, we'll start with the unit 1 and synthesis and modification of inorganic solids. And here also in this part of this module, we'll be focusing on conventional heat and beat method of the synthesis. Rest of the methods will be discussed in the second and third part of the module. The learning objective of this particular subunit of this unit 1 is, after studying this unit, you are expected to uh, at least list 6 different types of solid state synthesis method and their applicability. You should be able to cite the main consideration for choosing a certain type of method for a specific system of reactants and products. You should be able to understand and cite the criteria that are important in material selection. Material selection as in what kind of reactants you'll be choosing, what would be the reaction atmosphere, what should be the heating range for a particular type of reaction, and you should be able to explain the generalized mechanistic steps involved in this discussed solid state synthesis method. So solid state reaction is also called conventional heat and beat method or ceramic method or shake and bake method. As we'll discuss the details of this reaction, you'll be able to understand why so many names are there for the same type of process. So solid state reaction is a direct reaction between two or more solids to give a final product. So in principle there is no decomposition is involved, but there are certain examples present where precursors or the reactants, the solid reactants, are chosen in such a way that they decompose during the reaction, and uh, uh, which enables the thorough mixing of the reactants. So we'll discuss this example later on. Solids, as we know, are thermodynamically very stable material, and they do not react at room temperature. Even if the thermodynamics of that reaction is favorable, but because of the very slow kinetics, very slow movement of the reactants or ions, the reaction visibly does not take place. It may take place in like 5 or 6 years after the contact, but in the realistic time window, our observation will be the solids are not reacting. So it makes it imperative that high temperatures are applied so that the solids can be made to react. The solid state reaction are simple to perform because they do not require very um, um, they are simple to perform, and these are considered clean reaction as other elements are not involved in making these processes, and that is why these are popular among industries. Like in liquid state reaction, we usually have a huge buildup of solvent because our solutes are quite less in number, so reactant and product both are soluble in solvent. We have to take care of the solvent, we have to take care of the impurities which are also soluble in that solvent. In that manner, these solid state reactions are considered to be simple and clean reaction because we are not going to use any solvent. Usually the byproducts are the gaseous products, and these gaseous products escape during the reaction, and we get a very clean and purified product in general after the completion of reaction. That way it is called clean reaction, and that is the reason that this process are quite popular among the industries. So in traditional ceramic method or solid state reaction method, we have to do the mixing and grinding of the precursor, which are also solid powder. So constituent oxides, carbonates of the reactants. So we can take our reactants in the form of oxides or carbonates. Usually sulfates are not preferred because they are stable, stable at even at very high temperature. So what we do, we take the, usually we try to choose the oxides or carbonates of our reactant, or according to our reaction scheme we mix and grind this powder so that we can achieve a very small size of the constituents of the reactants, and then we heat them or fire them at a very high temperature. That is why it is called shake and bake. So the mixing and grinding part correspond to the shake Shake and bake is like we have to carry out the reaction at very elevated temperature, and sometimes the grinding in between the reaction is also important so that the product buildup can be minimized. This point will be clear will be further clarified in the next slides. The solid state reactions are governed by heterogeneous reaction concept, because a homogeneous type of mixing which is seen in traditional liquid state reaction, it is absent here. The reactants are not mixed in an atomic level, but the particles of the reactants are mixed generally at micro level, and therefore these reactions are inherently slow because the mixing is not at atomic levels. So the reaction proceeds by hopping of the constituents ions from one reactant to another reactant, and if the product buildup is there, which is generally there, then the reactant ion has to hop through the product also. So these reactions are carried out at very high temperature, and sometimes the controlling of the reaction atmosphere is also imperative. Why? Because it may happen that uh, your material has a tendency to react with CO2 gas or air or oxygen in the air. In that case, you have to carry out your reaction in an inert atmosphere. You do not want oxygen related defects to be produced in your final product, so you have to control the reaction. That is just one example why the control over the reaction atmosphere is required. Sometimes in a particular atmosphere the reactant are not stable, or the product are not stable at that elevated temperature, then also you have to control the reaction atmosphere, and you have to also control the rate of flow of that gas which you are using for maintaining that reaction atmosphere. So the product which is being formed during the solid state reaction is usually formed at the interface of the reactant A and B. So sometimes it is the governing rate, that governing rate of reaction is mm, the diffusion of the ions through the product and through the interface of reactant and reactant A and B. So this product buildup is affected by rate of diffusion of components at the interface, and this will give the kinetic control to the uh, solid state reaction. So thermodynamically, even if the reaction is feasible, we have to elevate the temperature, we have to ensure the mixing of the reactant at a very low level, and also we have to look into the consideration of what is the rate of diffusion of ions through this interface. It, even the thermodynamically favorable solid state reactions are observed to be non-spontaneous, and they exhibit kinetic control. The first step in the reaction is the formation of nucleation sites or nuclei. These nuclei are very small crystals of product, but if you compare it with a single unit cell of the product, it is quite large. It is typically of the order of several tens of angstrom, and on this nuclei the further growth of the product takes place. If the nuclei itself is destabilized and disintegrates, the reaction will not move further or in the forward direction. The product form will disintegrate immediately, either back to the reactant or something else which you were not interested in to begin with. So for a reaction to proceed in the forward and the favorable direction, it is required that the nuclei must be stable, and because of the very small size of the nuclei, they have very large surface area to surface volume ratio. Therefore their surface energies are quite high, quite positive and big in number, and they tend to exceed the free energy of formation of product. So for a stable formation of a stabilized nuclei, it is required that a balance is established between the surface energy as well as the free energy of formation, so that reaction can proceed in the forward direction. The various factors which contribute or control the reaction rate directly in a solid state reaction are the mole fraction of reactants, the time of reaction, particle size, reaction atmosphere, diffusion coefficient of reactants and products, and thickness of the layer of the product or the product buildup. So, how does mole fraction of reactant affects the rate of reaction or control the rate of reaction? As you know that reaction takes place at the stoichiometric level. So, if for example, if you need 1 mole of A and 2 moles of B, then at least 2 moles of B should be present for the reaction to complete and to take place and form AB2. If you are taking B in a lesser amount, the reaction will take place till all of the B which is required for the reaction to complete is exhausted in the reaction mixture, and you will be left with the reactant A which has no reactant B to uh, react with. And in that case, what would happen, that reactant itself uh, will be present in your final product. And since A and your product both are in the solid form, so it is very hard to separate now this unreacted reactant from the product. So that will cause a further problem, because how do you purify your product? So it is required to calculate all the stoichiometries and the mole fraction of the reactants according to a balanced chemical equation, mix them in the same ratio and then proceed for the reaction. The reaction time is also very important. As I have mentioned it already, the reactions are inherently slow in nature, because one solid reactant, if you can pay attention here, if your reactant is one reactant is A and another reactant is B, I'm focusing at the extreme right side and the bottom of the screen. This reactant A has to go to reactant B to form product, or B reactants molecules or ions have to, usually it is ion have to diffuse through the interface to form a product with uh, reactant A. So this to and fro movement of both the ions is very much required for a solid state reaction to take place. And at the interface of A and B, the product is being formed. So initially the layer of the product will be very thin, but eventually the product will grow and this layer will thicken. So if the mobility of ions of constituent ions or the reacting ions of A through the product layer is not fast, or they are not able to diffuse faster, the reaction will slow down. So in that case, you have to be mindful of the time which you have to give for your reaction to take place or to complete, and it may be required that you have to grind this material again in between the reaction, so that product buildup layer is removed and now the fresh interfaces between A and B, which are the reactant, are formed and the reaction can then take place. That is why also the particle size of the reactants has to be very small. If we have a very small particle size, the mixing um, it is not going to be as good as the mixing at atomic level, but still you are providing a very high surface area for the reactants to interact. And because of very small size, the interface will offer least resistance for ions from A to hop into B, or from B to hop into A side, and the reaction will take place. The reaction atmosphere is also important, because if the reaction involves, um, for example, there is CO2 gas which is being emitted or it is being produced as byproduct. So CO2 gas will also be they present in the reaction mixture, and it will be coming out of your reaction vessel, and in your atmosphere also. If the atmosphere is air, there is also some CO2, because it is there in the as a one of the major one of the significant constituents. So that the CO2 extra which is present there may reduce the rate of reaction as in accordance with the Lichtalier's principle. Or sometimes it might happen that the product you're trying to form is unstable in presence of air or oxygen, and it is prone to oxidation. So there is a chance that few oxygen deficiencies are being produced in the product which you did not want. Or it could happen the product may take few oxygen as oxide ions, and they will settle in the interstitial sites and they change the stoichiometry of the product, or may create some defects in your final product. So that is why sometimes it is very important to control the reaction atmosphere. And diffusion coefficient of reactant and product is also important. As I explained earlier, the reaction takes place by diffusion of the ion from one reactant to another reactant site, and product is also there. So product, the ions have to move through the product barrier also, so you have to take care of the product buildup during the reaction, or at least you should be aware that how it is going to affect your reaction rate. So to stabilize the nuclei, uh, we have two ways. Either we provide a heterogeneous surface for the growth, or we use the material as in the reactant which have similar crystallographic orientation, that is their major structure feature of the reactants are preserved in the product. So if they are preserved in two dimension, we call it epitaxy, and if the major structure feature or the crystalline nature of at least one of the reactants is preserved in three dimension, we call it topotaxy. Let us understand this thing by taking the example of formation of spinel MgAl2O4, which is formed by the reaction between MgO and Al2O3. This particular example has been adapted from the fourth chapter of solid state chemistry and its application by A.R. West. These magnesium ions in MgO, they fully occupy the octahedral site in MgO, and in the final product with the spinel product, they occupy 1/8 of the tetrahedral site. The more importantly, the O2 ions, that oxide ions, in these reactants in MgO, these are in CCP arrangement, and in alumina these are in HCP arrangement. The stacking sequence is HCP in Al2O3, and in other reactant which is MgO, their stacking sequence is CCP. Now the oxide ion in the product, it is also stacked in the CCP arrangement. So it is easier for the reaction to take place from MgO site, because one of the constituent of the reactant as well as product does not has to undergo any specific reorientation during the process. And so this similarity in the structural feature also makes it easy to form this product nuclei on the MgO surface. On this right side of the diagram where the pointer is placed right now, you can see this magnesium, which is an octahedral site, and this is magnesium oxide, and this is the substrate, and on this side the product is being formed. So this is here the magnesium is undergoing a structural change. It is going from octahedral to tetrahedral site, and aluminium, which is already in octahedral site, will be present in the product in the octahedral site. So no much rearrangement is required, so energy requirement for the product formation goes down. And the oxygen which is present, so not the oxygen, the oxides which are present in the MgO are in CCP sequence. Similarly in the product side, these are in the CCP arrangement. So that is why the reaction can move without much difficulty, or without optimization of the reaction condition, and especially it will be formed from the MgO surface site. You can see here the first interface will be between MgO and aluminum oxide. Then the movement of aluminum will be towards this side where it can interact with MgO, and the magnesium ion will move towards alumina side, and the reaction will take place. And at this place, the product will start building up. So how do we set up a solid state reaction? So far we have understood what are solid state reaction and what is the key step or first step in the process of a solid state reaction. What are the key factors which affect the solid state reaction? And now we'll be moving towards more realistic condition where we'll be discussing how the solid state reaction is set up. So first is we have to increase the area of contact between the reactants. So this can be done by reducing the particle size. So traditionally it can be done with mortar pestle. You have to use your elbow grease. You mix your A and B component or any number. Usually it is 2-component or maximum 3-component reaction. They will be mixed thoroughly by grinding in the manual mode. And same can be performed very efficiently and without much of the human labor using this uh, equipment which is called ball mill. Here, as you can see, there are small balls of ceramic material, usually zirconium oxide, are present, and these balls are of various sizes. You'll mix your reactants, or you'll put your reactants within this in this chamber. Then this chamber is moved at a specific RPM, that is rotation per minute, for the time which you'll choose. Usually it is 8 hours, 12 hours, depending upon the reactants you are taking. And the reactants will, as the drum moves, this is an older arrangement. Usually now in this new instruments, it looks different. The reactants will be coming in between these balls, and they'll be churning while the drum is being rotated. And because of the agitation provided and the impact provided by these bigger balls, the reactant will break down into smaller particles, and they will also mix with the another reactant as close to homogeneous condition as possible in the solid state reaction. But a problem is that if you carry out this ball milling process for a long duration of time, the material may heat up and the reaction may take place within this ball mill instrument also. So you have to be careful in choosing the time and RPM for the breaking the particle size. If your intention is only to reduce the particle size, you have to be mindful of that. Another method is spray drying. Here, the reactants are dissolved in a suitable solvent, and they are, if you pay attention here, the core material or the solvent and the shell material. We won't say it is a shell material, and this image has been taken from internet. We'll be taking our reactant A and B, and they'll be mixed in the solvent, and then heated air or gas is passed through this chamber, and the material which you have mixed, your reactants you have mixed or made a paste or slurry of, that will also be charged here in this drying chamber. So the solvent and your reactant will come into this chamber, so is the heated air or gas. The flow of gas will ensure that the particles remain in the form of a very fine or fluffy powder, and also the heated air will ensure that the solvent is evaporated because of this heat provided by this heated air or gas. So the exhaust fan is there so that the solvent vapors and the air could escape, and this cyclone powder collector will collect the fluffy powder of your reactants. So this very fine powder is then again heated to give the products, heated under the reaction condition of temperature, the heating rate, and if the atmosphere control is required, then that should be provided, and the product will be formed. This is one of the ways of making sure that the particle size of reactant is reduced, as well as the mixing of the reactants is also uh, ensured during this process. Another way of doing the same is using the freeze drying method. Here reactants are dissolved in a suitable solvent and they are frozen to liquid nitrogen temperatures. Then solvent is removed by pumping to leave a fine powder. So vacuum is applied and the solvent evaporates, and the mixing which was done in the solvent phase will ensure that the fine powder of your reactant mixture is obtained, and then this powder is further used for reaction. So to ensure that the contact between the reactant is there is a close contact between the reactants, so that an interface could be formed and reaction could take place at the elevated temperature. Sometimes it is required that we pelletize our reactants. So this is a typical pelletizing machine or hydraulic, it's sort of hydraulic press, and this is called dye. Here this powder is put and it is put here, then, and this hydraulic press, high pressure is applied which converts this powder into this solid pellet. So in this pellet, already the mixing of the reactants is done here in the form of fine powders, but this pellet will make sure that the reactants are in close proximity, and these pellets are further heated at elevated temperature to bring out the reaction. So how to heat the material? Now we are talking about the reaction condition. So there are several ways. Um, First of all, how should we contain that sample? So these are, if you pay attention to the cursor here on the bottom of the slide, so the container of the reaction are usually called crucible, and they should be able to withstand that high temperature A. B, they should not react with the reactant at elevated temperature, and most importantly, the container or the reaction vessel or crucible should not react with your product also. So you have to keep that in mind while choosing a particular reaction vessel. So this is a quartz boat, this is a platinum boat, and we can have silica crucible, we can have alumina crucible as well. So you can see here silica crucible is stable up to 1430 Kelvin. Alumina has more stability, it is stable up to 2200 Kelvin. Zirconia is 2300 Kelvin, and platinum is stable at 2045 Kelvin. Silver melts at 1235 Kelvin, but if you are reacting your material at a lower temperature, the silver boat is also quite useful. Uh, so this notch you can see there, or this ring um, is there in these boats, because if you are putting your sample in a tubular furnace like this is called tubular furnace. So in this tube, you will insert your boat which will contain your reactant. So because since you have this ring, so here you can have your so in this boat here you can push and pull the boat using one long steel rod with which is bent at a certain edge, because otherwise how you will put your material in this tubular furnace. So that is why this ring is there. And if you are using a furnace, there you can place this boat directly, or a simple boat can be placed here directly. So you can have this type of furnace, or you can have a tubular furnace. In this tubular furnace, if you can see here, there is this pressure gauge. So this gives you an option of attaching one cylinder of nitrogen or argon or hydrogen or carbon dioxide or air, if you want to have the specific control over the reaction atmosphere for your reaction. And somewhere around you have to provide one exhaust channel for this gas which is being flushed in. So while you're maintaining the atmosphere, you have to look into the flow rate also. It should not happen that the reactant which is placed inside this tube should escape your reaction vessel, because if gas is being flushed at a very high rate, so the fine powder may spill out of your reaction vessel. It will not only contaminate your uh, furnace, but also it will change the mole fractions of reactants in the reaction your product. So this is one interesting example how from one of the article published in 2012. It's a relatively simple simple solid state reaction. So here gypsite, which which is an ore of aluminium, is made to react with cobalt chloride hexahydrate to form cobalt uh, CoAl2O4, mixed oxide of cobalt and aluminium. And these are nanoparticles, and their applications are in inorganic ceramic blue pigment, which is used for coloration of plastic, paint, fiber, rubber industry, and ceramic bodies and porcelain and enamel. So in this particular research article, the authors have seen the difference of the particle size of the reactant, the 13 micron and the zero point 0.6 micron, when they have reacted the same material gypsite with where the particle size was 13 micron is 10 raised to power minus 6 meter, and when they fine grinded it into 0.6 micron and reacted with the same reactant, they obtain different product. Here you can see that the appearance of the product itself is different. The blue here and the blue here are giving the different tinge. So same material, same reactant, but the particle size, when it was changed, the physical chemical property, and in this case the optical property of the same material changed. So what they have done, they have taken gypsite and they ball milled it to get a fine powder of 13 micron size. Then they again ball mill this 13 micron size for 24 hours to reduce the size to 0.6 micron, and they have seen the reaction with the cobalt chloride hexahydrate. So first on their reaction, this dark colored or charcoal colored product was formed, and then after calcination at 450 and 650 degrees centigrade, the products which were formed are of different color completely. This example is being discussed just to make you aware that how the particle size affects the final property of your. So third part of the setting of a reaction includes the consideration about the reaction atmosphere and how it can be controlled. Sometimes it is required that the product or the compound must be formed under a special atmosphere. It could be a noble gas if you do not want your product to go into higher oxidation state, or if it could be oxidizing gas like oxygen, because you want your product to be in high oxidation state, or you want to create some oxygen related um, defects in your product to tune their electronic property, or your intention could be to reduce the oxidation state to lower side, then you might be using hydrogen as the reducing gas. So as I've shown in the previous slide, this is the tube. Usually it is a quartz tube because quartz is quite stable even at a very high temperature. This quartz tube um, will contain uh, your reactants in a reaction vessel, and you will be flowing the gas. It could be any gas as per requirement of your reaction. Here I have taken an example of nitrogen, and after the reaction or during the reaction, it is required that you provide a pathway for this gas to come out of your reaction vessel. So exhaust, a channel for exhaust gas is provided, and usually we do not let the exhaust gas go directly into atmosphere. We trap it in a volumetric flask or a conical flask with closed mouth and some trapping liquid, so that all the byproduct, the gaseous byproducts which are coming out of this reaction chamber as well as your exhaust gases are not released directly into the atmosphere of the lab from the safety point of view. So having discussed that, let us have a look at the disadvantage of this method, which is ceramic method or solid state reaction method. Till now we have talked about that we need to make the material more homogeneous. That means there is a possibility of inhomogeneity uh, in the reaction, because if your reactants are not uh, made or not mixed or grind well, then there could be some segmented or localized reaction taking place at different segments in the same reaction vessel. There is a chance of contamination from the containers, because especially for the reactions which are being carried out at very elevated temperature, so some of the material of your reactant or product may seep into the pores, fine pores of your container at such high temperature, or something from the container may leach out into your reactant and product. Usually in the research lab where such reactions are carried out, you could see that although they have used the silica or alumina boards, there are some tint, some grayish or brownish or blackish um, stains on the inner surface of those pores. So that means some product or reactant has seeped into the structure of their reaction vessel, and in that case it is required that either they clean it at oxidative temperature or oxidative condition at very high temperature, and if it is not being cleaned, then it is suggested that not to use that same container for further reactions, because it can serve as a source of contamination. Sometimes, and usually these reactions are carried out at very high temperature, 500 to 2000 degrees centigrade, and that takes a significant amount of energy uh, consumption, because this energy is required to overcome the lattice energy so that cation and anion can hop from one side to other side. There is a possibility the compound or the product you are forming, it is not stable and it will start decomposing at the high temperature. Sometimes the reactants with specific characteristics which are required for these sort of reactions are not available or are very expensive. What do we mean by desired reactant? That the reactant A which are reactive, first of all, that means the diffusion coefficient of their ions are um, favorable. Secondly, as we have talked about the epitaxy and the topotaxy, that is the structural rearrangements as which are required for reactant to go into product are the requirement is as less as possible, so reaction will be favorable and it will be easily formed, as we have discussed for the MgNAl2O3 reaction case. And another thing is that our reactants or one of the reactants should not melt at the reacting temperature. For example, if the reaction between A and B takes place at 1500 degrees centigrade, both A and B should not melt at 1500 degrees centigrade, plus the product which is being formed at 1500 degrees centigrade should be stable there. It should also not melt or it should not decompose, because in case one of the reactant starts melting, so the reaction, the one will be liquid phase, another will be solid phase, so it will be subsolidus kind of uh, situation. So the mixing which we wanted to occur at the stoichiometric level, or the reaction which the mole fractions which we have calculated for the solid state reaction will change, because some of the reactant has been thrown out, and the reaction may not proceed as you have desired. The spillage and contamination of a furnace may take place during such reaction, because especially if one of the product is a gaseous product, so at elevated temperature the gaseous product will move out of the reaction vessel with force, that and it can lead into spillage of the reactant or the product from the reaction vessel. It will not only contaminate the furnace, but also it will again change the mole fractions of the reactants which you have already calculated for your reaction. For example, if A and B were supposed to mix in 1:2 ratio, and some of the B just comes out of your reaction vessel along with the byproduct, now the reaction will not go to the completion, and some of the A, unreacted A, will still be there along with your product. So practical consideration and key points to remember after this discussion are that solid state reaction may be easier if one or more of the starting material is chemically reactive, or it contains ion that can diffuse easily. We have to choose such reactant which have easy diffusible ion and very reactive, and ideal starting material should be of accurately known stoichiometry. They should be pure and reactive. The reaction temperature should be about 2/3 of the melting point of the lower melting reactant, so that the reaction uh, can proceed in the manner as you desire. It is also called Taman's rule. That, for example, if your reactant A um, and there is a reactant B, so the reaction temperature, ideally the temperature at which you have to heat A and B should be at least 2/3 of the melting point of A and B. So in case of A and B, if your B is lower melting, like B melts at 700 degrees centigrade, A melts at 1000 degrees centigrade, so you have to carry out a reaction in such a manner that your reactant B, with the melting point at 700 degrees centigrade, so it should react with A at a temperature much below 700 degrees centigrade. So should be at least 2/3 of 700 degrees centigrade. So 2/3 of the melting point of the lower melting reactant. So it is also called Taman's rule. So the starting materials are chosen keeping this point also in mind. The mixing of the reactant method should be optimized to ensure maximum contact between the reactants, because then the reaction will move fast, and the formation of product will be optimum, and your yield of the reaction will be good, and the product will be uh, there is a chance that product will be a very clean product. The reaction container and the vessel which you are choosing should be stable at that reaction temperature. It should be non-reactive toward both reactant and product, and that also includes byproducts. The reaction atmosphere and gas flow rate should be controlled as per the reaction's requirement.